Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to the concept of latent heat. And there's two of them that we're going to talk about, what's called the latent heat of fusion and the latent heat of vaporization. So let me explain what we're looking at here. So over on the right, over in this region here, imagine that we've got maybe an ice cube that we've taken out of a ice tray out of our freezer, and we put it in some sort of metal pan, and it's sitting on a burner. Now we've turned the burner on, and the burner we know has gotten very, very, very hot. And now, because the burner is very hot and the ice cube is relatively cool compared to it, we're going to get an energy transfer in this direction. Right, and that's what we call heat, and we usually represent that with the letter Q. So again, heat is energy transfer due to a difference in temperature. Now, over on the left, what we're looking at is a graph, and the graph is going to be the temperature of the ice cube against heat added. Now, the first point on the graph is an important one here. If the ice cube has just been taken out of the freezer, its temperature is definitely down below zero. You know, the inside temperature of a freezer, if I had to guess, it's probably, I don't know, maybe 10 degrees Fahrenheit or so below freezing point. So in degrees centigrade, you know, this is going to be some negative number now down here. So this point on our graph here represents the initial temperature of the ice cube before we heat it. Now, as heat transfer occurs, the temperature of the ice cube is going to start going up. And typically, especially if you add that heat very slowly, what happens is, or let me restate that, especially if you heat it slowly, then your temperature changes will be linear in nature. So the first part of this graph looks like this. We get basically a linear relationship between temperature and heat added. This distance on the graph would represent the temperature change. This distance would represent how much heat we've added to the ice cube. This point right here is a fairly special point. At that point, the ice is now 0 degrees centigrade, and 0 degrees centigrade is the temperature where ice will freeze, or melt, where ice will start to melt. Now, as the ice melts, a very interesting thing happens. You know, imagine in this picture here, we've got a little bit of puddle of water here, maybe right around the ice cube. If the water's temperature starts going up above zero, more ice will melt. That heat will transfer to the ice cube, melting more ice. So there's kind of a function here to keep that water from raising in temperature. So, you know, this is what we call a phase change when the ice goes from solid to liquid. And phase changes tend to occur at constant temperature, at least if we heat this ice very slowly. So on the graph, we're going to be moving horizontally to the right. This distance on the graph right there represents the energy needed to melt that ice cube. Right. Now, at this point on the graph, that cube would now all be melted. It'd be liquid water at 0 degrees centigrade. Right. If the heat transfer continues, the temperature of that cube is going to start increasing again. And again, it's going to go up linearly. So we're going to have another linear portion to this graph. And this linear portion will go all the way to here to the next very important point for water, which is 100 degrees centigrade. 100 degrees centigrade is the temperature where water will start to vaporize, meaning it'll change from liquid water to steam. As we move to the right, we're now vaporizing the water. And this point right here, we would have all of that ice cube would be steam at 100 degrees centigrade. Kind of backing up to this point, all of that cube would now be liquid at 100 degrees centigrade. And this distance on the graph represents the energy needed to change that cube. Well, at this point it's not a cube anymore. We'll say change that water from liquid to a gas. Right, this process in physics we call vaporization. Right? We're vaporizing the water. So at this point on the graph, that water would be all steam at 100 degrees centigrade. If we keep the heat transfer going, then the temperature will start going up, and again linearly. Now again, this is all assuming that we can keep this system all isolated and keep the heat going, or keep the energy transfer to the water without it escaping, etc. But that's not, necessarily practical with a completely open container. But all right, these linear regions, let me point those out. Here, here, and here. These are temperature change regions. And those are described by using what's called the specific heat. So hopefully you've watched my video on specific heat, and we know that specific heat is equal to heat over mass times temperature change, or usually in equation form. We write that Q equals mc delta T. Right? So this equation is good along these parts of the curves. Now you'll notice on the graph here that those three lines have different slopes, and I did that fairly deliberately. That's because the specific heat of ice and the specific heat of water and the specific heat of steam are not the same values. Even though it's water, the specific heat can change depending on the phase. The specific heat of water is around 4186 joule per kilogram degree centigrade in its liquid form. The specific heat of ice is around 2090 joule per kilogram degree centigrade. So you can see it's quite a bit easier to change the temperature of ice than it is to change the temperature of water. Right? The phase change regions, those are really important. So let's see, I'm going to do this in red. So this is a phase change region. This is a phase change region. There's no temperature changes there at the phase changes. The heat required to change the temperature depends only on the mass, and it's a directly proportional relationship. In general, we can say the heat is equal to some constant, that I'm going to write L for a moment, times the mass. The constant L is called the latent heat. Now, you can tell hopefully by the equation what the units on this would be. Right? Heat would typically be measured in joules, mass in kilograms. So the latent heat has units of joule per kilogram. Now any given material will have two different latent heats. One for going between solid and liquid, one for going back and forth between liquid and gas. The latent heat to go back and forth between solid and liquid is called the latent heat of fusion. It's usually written L sub F. For water, the latent heat of fusion is 3.33 times 10 to the 5th joule per kilogram. This is a numeric. This is a value that if you're in a physics class, is pretty important. You'll be using from time to time. Right. The other latent heat, the latent heat for going from liquid to gas, is called the latent heat of vaporization. Oops. For water, the latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. Now, one thing I'd like to point out right now, when you're looking at this, you'll notice that the latent heat of vaporization is about, I'd say about 9 times bigger than the latent heat of fusion. Not quite 10 times bigger, but about 9. And what that means physically is really important. It takes a lot of energy to vaporize a kilogram of water. In fact, it takes 2.26 million joules of energy to vaporize a kilogram of water. It only takes 333,000 joules to melt a kilogram of ice. So from an energy state standpoint, that means that when you have steam, it took a lot of energy to make it steam, and therefore it carries a very, very high internal energy. And that's why steam burns can be very, very potent. All right, so let me kind of overview this going back to the beginning. So in this example, we're looking at temperature against heat added for an ice cube. But lots of materials behave this way. This could be a chunk of metal, like aluminum or lead or something like that. And if we did kind of a similar graph for a chunk of lead, we'd get a very similar graph. We'd have a region here where the temperature is going up. We'd have a phase change region, another temperature increase, another phase change, another temperature increase. The only difference is that the melting points, the 0 and the 100 degrees centigrade, would be different for lead, and the constants and the numerical values were different. So when you're analyzing thermodynamic problems, you've got to be very mindful that you've got two different types of scenarios to consider. You've got temperature change regions, which are governed by specific heats, and you'll be using this type of relationship, Q equals MC delta T, and you have phase changes. And for phase changes, we're going to be using this relationship, Q equals L times the mass, but you got to keep in mind there's different latent heats. Most materials will typically have two latent heats, one for the liquid solid change and one for the liquid gas change. So I hope this video helps introduce these concepts. I think I'll stop now and make another one with some examples, and have a great day.